Good morning, I'm Manuel Zarzo. We are in Unit 8 Regression. Today in this video I'm going to talk about multiple linear regression. Okay, well, imagine that we have j observations of one random variable that we will call y. Okay, well, the values correspond to I variables. Okay, in this case we have more than one explicative variables. In simple regression we have just one. In multiple regression we have more than one that we will call x1, x2, xj. Okay, I will be the number of explicative variables. The j is the number of observations. Okay, these variables may be random or not. Okay, random means that I measure experimentally the value of something, and not random is when we fix the value of something, like in an experimental design. For example, I make some throwings or some launches of airplanes of type A and other launches of airplane of type B. Okay, in an experimental design that I fix, that would be a variable which is not random. Okay, so these variables may explain or not the variability of the y. So some of them might have influence, others might not have influence. So this is what we have. The variable to explain is random, is measured randomly, and then we have explicative variables or factors. Explicative variables are random, factors in a factorial design are not random. Okay? This is the case. Then we have the values measured for a set of observations. It's important that in multiple linear regression we can just use one single explicative variable. Okay, we will have just one. What happens if we have more than one? Well, imagine if we have three, we should fit one multiple regression model for every kind of the three explicative variables. This is one of the disadvantages. If we have a lot of explicative variables, we should use another techniques of multivariate regression. So the target is to study possible relationships between the distribution of the y as a function of the values of the different explicative variables. Okay, so we will call dependent variable, that is usually represented as a y, and then we will call explicative, independent, or exogenous variables. Okay, it has different names. Good. So the classical regression models assume the following. It's assumed that its observation is the observed value of a random variable y, which is normal. Okay, we assume that the variance is unknown but constant. This is called the hypothesis of homoscedasticity. Homoscedasticity, remember that it means equal variance. Okay, we also assume that the average of the y is a function of the observed values of the explicative variables. Okay, we will write that the expected value, the expectation of the y is a function of the explicative variables. Okay, it's written like that. So the average value is a function. We also assume that the variance of this conditional distribution is constant, hypothesis of homoscedasticity, and then we also assume that this conditional distribution is normal. Okay? The conditional distribution is normal. Okay? It can be written like that. The expectation of the y for given specific values of the explicative variables, okay, is given by this, by a linear combination of the explicative variables. This is the classical mathematical model of multiple linear regression. We have a constant that is usually expressed as beta 0. Then we have a coefficient that multiplies x1. We have another coefficient that multiplies x2, and so on. We have another coefficient that multiplies the last variable. These coefficients are called beta. Remember that Greek letters are used at the population level. Okay, Here, writing beta means that I refer to the constants at the population level. So equation of the model. What is the interpretation? When all explicative variables are 0, okay, so the expected value is beta 0. So the interpretation, the practical interpretation of beta 0 is the average value of the y when all the explicative variables is 0. And then what is beta? What is beta? Okay, beta, the practical interpretation, is the increase in the average value of the y when x increases 1 unit. For example, beta 1, what is the interpretation of beta 1? The average increase of the y when x1 increases 1 unit and the rest of explicative variables remain constant. Okay, that is important. Mathematically, that would be equivalent to the partial derivative. So if I make the partial derivative of this mathematical equation with respect to x1, okay, that would be beta 1. Okay, stages in a regression study. Okay, first we have to formulate the model. Okay, we have to provide a precise definition of the dependent variable. Then we have to select the explicative variables that we can measure or we can have information. Then a selection of the analytic equation for the model. Good. Then if some of the variables present skewness, strong skewness, maybe it can be necessary to apply transformations. Okay. Then the second step would be to collect the data, to collect experimentally the values. Then once we have the values, we have the model calibration. So we have to fit the mathematical equation of the model to our values using a statistical software. Okay? Then the software provides an estimated coefficients for the regression, for the constant and the regression coefficients. Okay? All coefficients are estimated using a statistical software. Imagine that this is an example. Good. So, and then model validation. How should we validate the model? With the analysis of residuals. So in multiple linear regression, so the last step is the analysis of residuals in order to validate the model, in order to make sure that the model is useful to make predictions. Okay. So by definition, residual is observed value minus predicted value. In this case, the observed value of the y minus predicted value using the mathematical equation of the regression model. Okay, so we should compute all the residuals, which is made automatically by the software, and then we should study the distribution of the residuals. That distribution should be normal with an average of 0, and that distribution should have a variance not dependent on any of the x, because we have to check the hypothesis of homoscedasticity. Okay. Also, we have to check that residuals are independent among them. Okay, so if we check the time series of residuals with respect to the time, so every value should be independent with the previous ones. Okay, so are they normally distributed? Is any outlier detected? So that is what we have to study based on the analysis of the residuals. Can we assume or admit the hypothesis of homoscedasticity? These are important answers that we have to, these are important questions that we have to answer in order to validate the model. Okay, is just linear the relationship between x and y for every x? Yes, this is also important because there might exist quadratic effects for one or more than one variables. Okay? And then once we have validated the model, we can use the model to make predictions. Regarding the model validation, it's important that in multiple regression, it's validated based on analysis of the residuals. In another video, I will explain that there are other kinds of regressions that use other procedures for model validation. So, study of quadratic effects. Imagine that I have a y as a function of x1, and we have a quadratic effect like this, a curve that might happen quite often. So we will say that there's non-linear relationship. Okay? Then it can be approximated by means of a second-order curve. Imagine that we just have the y that is a function of just one x. Imagine that we don't have more than, we just have a single x. So we can fit a model like that: a plus b multiplied by x plus c multiplied by x squared. Okay? So in simple regression, this is the weight as a function of the height. This is an example that I explained in a previous video. Okay? The r squared, the coefficient of the determination, in this case is 0.55, so it's more or less a moderate goodness of fit. Okay? But if we apply multiple regression, okay, we find that these are the estimation of the regression coefficients. We have a small coefficient that multiplies height squared. The goodness of fit in this case is 0.56, so it is slightly higher. So we can see that the quadratic model explains or fits the data slightly better than the linear model. So can we say for that reason that the quadratic model is better than the linear model? Well, the answer is no. The answer is no. This is the table of results for this multiple model. We have height, we have height squared. This is the estimated values of the coefficients, and then this is the intermediate calculation that leads to a t-statistic, and based on this t-statistic, we have some p-values. Okay, so then what is the procedure to determine which model is better, the linear model or the quadratic model? Okay, well, so this is the theoretical model that we're fitting. At the population level, we have coefficients beta 0 plus beta 1 multiplied by x plus beta 2 multiplied by x squared. Okay. So every time that we have a p-value, we have a null hypothesis associated. Okay. For the constant, the null hypothesis would be beta 0 equals 0. For this second p-value, the null hypothesis would be beta 1 equals 0. And for this one, the null hypothesis is beta 2 equals 0. Okay, then what is this p-value? It's 0.038. Okay, well, remember these equations you have in your mathematical math tables. I explained this in a previous video also. So we have a null hypothesis. Okay, we have the calculation of t, which is the estimated value of the coefficient divided by the standard error. That leads to this t calculated, okay, this one. It follows a student t distribution with n minus 1 minus I degrees of freedom. The I is the number of variables included in the model. In this case, we have 2 variables included, okay. Then, based on this value, if it is frequent value, we cannot reject. If this value is not frequent, we will reject. So we have a p-value that we have to compare with alpha. Remember that this rule is a general rule that we use in statistics for any kind of inference test. So if the p-value is less than alpha, we will reject the null hypothesis. If the p-value is bigger than alpha, we cannot reject the null hypothesis. Okay? And then what happens in this case? It's interesting because the p-value is 0.038. So what happens if alpha is 5%? So this value is, the p-value is less than 0.05. So if alpha is 5%, which is very common in statistics, we can reject the null hypothesis, and then we can say that this coefficient is not 0 at the population level. So we can say that there is a quadratic effect at the population level. Or we can say that the quadratic effect is statistically significant. Okay? So the quadratic model is better for alpha 5%. But what happens if we assume alpha 1%, which is also quite common in statistics? Then we can see that 0.038, okay, the p-value is bigger than 0.01. In that case, the p-value is bigger than alpha, so we cannot reject the null hypothesis. We cannot reject means that this coefficient has to be considered as 0 at the population level. we don't have enough evidence to say that this coefficient is not 0. So it should be considered as 0. Then this term goes out. So we should remove the quadratic term out of this equation, and then it just becomes a straight line. Then we will say that the linear model is better for alpha 1%. Okay, so this is a very interesting result. So which model is better, linear or quadratic? The answer is that it depends on the alpha. Okay, now we have the table that is called analysis of variance. Okay, it is provided by StarGraphics, and then we have a p-value. Remember, every time that we have a p-value, we have a null hypothesis associated. So, and what is the null hypothesis in that case? Well, it's called the global significance test of the model. Okay, so it's called analysis of variance. So, and what is this global significance test? Well, this is the null hypothesis. The null hypothesis is that all coefficients that go with the variables, look, it's important that the beta 0 is not included. All coefficients except beta 0, all coefficients are 0. The alternative hypothesis is that at least one of them is different from 0. Okay, so it's like more or less analysis of variance in the sense that we have a sum of squares, we have mean squares, we divide the mean squares of the model divided by the residual. We have an F ratio that we compare with the critical value from a F table. Okay, so from the F distribution we have a p-value. So if the p-value is very small, we reject the null hypothesis. It means that at least one of the coefficients is not 0. So it means that the model is able to make predictions. So the interpretation of this p-value is that if it is very small, if it is less than alpha, the model can be used to make prediction. The model globally is valid. But if this p-value is bigger than alpha, means that all coefficients can be considered as 0. It means that the value is not valid. It cannot be used to make any kind of prediction. Okay? And also, based on this information, we can compute the coefficient of determination. Remember that in a previous video I explained how it was computed as 1 minus the variance of the residuals divided by the variance of the y. Well, based on this information provided by this table, the coefficient of determination can be computed as sum of squares explained by the model, which is this value, by total sum of squares, which is this value. Okay, if this value is high, means that the goodness of fit of the model is high. The maximum value is 100%. And important also, the mean squares of the residual, this value is the estimated value of the variance of the residuals. Okay, so which is important because in the exams sometimes this value is used, as I also have explained before. Okay, so I can compute the residuals, I can save the residuals and then compute the variance of the residuals. But if I have this information, just taking the mean squares of the residual, this is that information. Okay, so as I was explaining, in this case the p-value is very small. It implies that at least one of the coefficients multiplying the variables is not 0 at the population level. The model is useful to make predictions. Okay, well, now in this case it's multiple linear regression. You have 3 explicative variables. All of them, the p-values are very small, are smaller than 0.01. So an exercise could be to write the model equation. So that would be constant plus this estimated value multiplied by x1 plus this estimated value multiplied by x2 plus the third estimated value multiplied by x3. Okay, in this case, before writing the equation of the mathematical model, I have to check that all p-values that go with the variables are less than alpha. Why? Because if one p-value is big, okay, bigger than alpha, I should discard that variable and repeat the model and fit the model again. So always that we use a regression model like this one, okay, always that we recommend a linear regression model, is that when we can ensure that all coefficients that are included in the equation are different from 0 at the population level. If we cannot ensure that, well, that variable should go out. So all variables in the final model should have coefficients different from 0 at the population level. Okay, so this is very, very important. So how to include qualitative variables? Okay, example. The yield of a chemical process depends on the type of raw material. Imagine that I have just raw material A or B, okay? And we have also temperature as explicative variable. Well, so we should create an indicator variable. It's also called a dummy variable. So that variable is created like following. So for raw material A, so the Z, for example, can take the value 0. For raw material B, this Z will take the value 1. Or I can define it in the reverse way. It doesn't matter. Okay. So by coding this in that way, so I can introduce qualitative variables into the regression model. And then even I can make interactions like this one. Okay. This is temperature. This is the indicative variable, and this one is the interaction between the temperature and the indicative variable. What is the interpretation of that? Well, now, what would be the fit line for raw material A? So for raw material A, the Z is equal to 0. So I go here, I make Z equal to 0, so it goes out. I make Z equal to 0, so it goes out, and then I have just this. So this would be the straight line corresponding to raw material A. And what happens for raw material B? In this case, the Z is equal to 1. Okay, from raw material B, Z is 1. So I go here, I make this 1, I make this 1, and then so as this is 1, this is a constant that can be added to 50. Okay, 50 plus 20. And if this is 1, the slope also increases. Okay, so what we have is another equation with a different constant and a different slope. Okay, so if all coefficients of this model are statistically significant, so that would imply two lines with different slope and different ordinate. And then the interpretation will be this one. Okay, so 50 would be the constant or the ordinate corresponding to raw material A. 0.5 would be the slope for raw material B. 20 is the increase in the constant. Okay, the increase in the constant, and 0.1 is the increase in the slope when the raw material is the B. Okay, so we can see that there is like a practical interpretation of all the coefficients that appear in this equation. So in case of three materials, can we use an approach like this one? Well, the answer is yes. Okay, in case of three raw materials, we should use two indicator variables like this one. For example, for raw material A, so the ZA will take the value 1, and for others 0. And so I will call ZB, that takes the value 1 for data corresponding to raw material B, and for 0 for the rest. Okay, so this is interesting because when we have a qualitative variable, the number of variables like this of this type that we have to create is the number of variance minus 1. Okay, important. In this case, we have just two raw materials, so with one dummy variable is enough. In this case, we have three raw materials, so it's necessary to use two dummy materials. Remember, it's always number of raw materials minus 1. And here, I finished this video about multiple linear regression.